Yes. Okay. So by the rising head option, which is down in the panel of instruments, if you do not find it, you can just ask by voice. We do not have a very firm restrictions in time, and that's why all questions after the talk are very welcomed, and also maybe small discussions. And I think the lecturers would not mind if I encourage listeners to contact maybe directly today's speakers by email after the lecture if they got interested in the subject. All lectures will be recorded, and after some formalities, we'll try to put them in the open sources. The last but not least, most of our speakers today and tomorrow have much teaching obligations this semester. And I know that some of them even have talks just after their lectures in universities without any break. But anyway, our speakers found it possible to participate in our workshop and deliver their lectures. And we greatly appreciate it. Now let me announce the first talk, the Professor Harmut Prautzch. He's known to everybody who works in subdivision and surface modeling, because he was one of the founders of modern subdivision theory. And personally, for me, I got interested in the subject, it was very long ago, with two papers of Professor Prautzch. So one of them was more or less about the subject of today's lecture, about the cutting angle of polygons and polyhedra, piecewise linear generation of surfaces. So the other one is famous work of uniform refinement of curves by joint work with Charlie Michel. So please, Professor Prautzch, so now it's your turn. Yeah.
Okay. Thank you, Vladimir, for the introduction, and thank you for inviting me to this workshop. It is the first time I am in Moscow, and in fact, the first time I'm in Russia, at least virtually. And so I have to visualize my audience. Maybe it looks like this. Or maybe now it looks more like this, in front of a big screen, a group of individual people sitting in front of their own device, big or small. And I was surprised to find hundreds of pictograms under the keyword video conference. So today we are going virtual, and we also make it more abstract by using these pictograms. So I decided to give you a pictogram of my talk. So this is the title of my talk. It is on cutting convex polyhedra. You see a cube that has been cut. Here's the cut, and it is a fresh cut. The blood is dropping down, standing for this is work in progress. So what we want to do is we wish to cut it and cut it over and over again, and hope to get something nice in the limit. So something like this one, which has been obtained by cutting a cube. However, this is not that simple. You need to know how to do it. And when we first started, it was more looking like this, where we said, well, we always cut the sharpest edge. But you see, it is not really a fair surface. This is done by some scheme. It's still no good. And ugly for the surface is convex. It's even C1, the ones that you see here. But these two features, C1 and convex, well, we connect them to something nice, but this is not the case. The rule is they are ugly, and nice is the exception. So we are looking for this exception and how to get it. And so far, at least as I know, there's no paper, no published paper on how to do this or on similar things for cutting these polyhedra. Some authors call subdivision schemes for surfaces corner cutting schemes, but they are not in this sense of cutting by a planar knife. However, we have several papers when it comes to curves. So for curves, cutting polygons in the plane, we know pretty much very well how to do it. And why don't we have papers on surfaces? So there are two reasons, I think. One is there are some intrinsic geometric problems from going from the plane to the space. And the other reason, somewhat related to the first, is for curves, we have a number of well-known schemes, corner cutting schemes. Not insertion for splines, subdivision like Lane-Riesenfeld, Chaikin algorithm, or Lane-Riesenfeld or Chaikin, the Castle-Joes algorithm, degree elevation. These are well-known and daily use, basically, algorithms that we have, and so there is some incentive to do something on it. For surfaces, however, there are no schemes, no standard schemes, and so this has not really been looked at. And I tell you what I did here and what we found out. And I will start that talk, since it's a more general talk. I was asked to talk to say something about subdivision. I will start like any other general talk on subdivision. They start with the Chaikin algorithm. I do the same, however, a little bit more general. As you can see, we are looking here at a planar polygon. And this is a result by Gregory and Xu from 1988, was published in 96, much later. So we take this polygon, we pick points on the edges of the polygon arbitrarily, doesn't matter where. And then we use these points. So we pick 2 points on each edge, and then we cut the corners by connecting the points that we have chosen. These 2 points on each edge, they define ratios, or are defined by ratios. So we have 2 numbers basically telling us of how to cut that edge. And these numbers can be different for any edge. And once we have cut the polygon, we will repeat it. So we also cut the corners of the new polygon that we get. And then we ask ourselves, what do we get in the limit? Is it a smooth curve? And Gregory and Xu, they have a very nice general result on it. If we consider these numbers, alpha and beta, in the alpha beta plane, then we find a certain, then any of these ratios and cuts corresponds to a point in this plane. And if I always choose my ratios out of this region that we see here, then we get a C1 curve in the limit. So this is the C1 region for getting nice curves. So it tells us there's not only one scheme, there are many schemes. There is a continuous set of infinite many schemes that give us C1 curves. Of course, there are other cuts that we can do. And if we consider this here, this big triangle that I have here, then this contains all the points that could be used to cut that polygon. And for some of the points in here, we know if we repeated that, then we know we do not get a C1 curve, but we could also pick ratios out of here and still get a C1 curve. So there is a more general result by Carl de Boer. And for that one, we would be using that here we are dealing with convex curves. So that makes things a little easier, because for convex curves, we have that C1 is equivalent for the corner not for the curve not to have corners. So it means no corners. And this is basically, if you have a convex curve or convex function, then it has a monotone derivative. And if there are no jumps in the derivative, then it is differentiable. And the jumps correspond to the corners. So we can use this. And Carl de Boer in 1990, he has shown that we have no corners in the limit if and only if the maximum angle that we have in the polygons, so maximum angle, goes to 0. However, here we need to assume something. We do this only for what he is calling local cutting, and I call it edge preserving cutting, and I explain it. So this is under edge preserving cuts. What happens if we cut in this fashion? We cut corners, but we don't cut edges. So on any edge remains partly at least. And if we keep on cutting, it will at least have one point that is never cut. So on every edge, we find a point that is never cut. Maybe we find even a complete segment that is never cut. There are points. And since I cut all the other edges too, otherwise I don't get the angles small, I find points of the limiting curve also on these edges. So the limiting curve goes through the points, and more than that, the edges of the polygon are tangential to the limiting curve. And that means we have a bound on the tangent in such a curve segment running from that contact point to this contact point. We go from that edge to this edge, and they turn around some angle. This is an angle of the polygon. So the angles of the polygons bound the normal variation for segments of the curve. So we have neighborhoods for every curve. The angle goes to 0. We have neighborhoods with arbitrary small normal deviation, variation. And that means we have a C1 curve. So the proof is simple. It's basically a trivial result, you could say. So what happens if we don't do edge preserving cuts? If we allow ourselves to cut more general, then this doesn't work. If we cut a little bit more, we can get counterexamples. And here you see such a counterexample. We start with a polygon, the black one, and let us get this yellow polygon in the limit. So we need to cut. And what I do is now I allow myself to do such a cut where I cut one corner, but I start at a corner. So I cut this edge basically too. And then I can repeat it in this direction. So what I get then, I get a cut where I cut one edge at a time, and I move the edge parallelly to what I had before. I move it parallelly, and I will move it so to half the distance to the limiting surface, limiting curve, limiting polygon, limiting area that we have here. And I do this for the other edges also. So I get closer to the limiting surface, limiting curve I reduce the distance by 1/2, and then in the next step, I would cut so as to make the angles smaller. I halve the angles. So there's a step where I move closer to the limiting curve that I have in mind, and there's a next step where I reduce the angles. And I can keep on doing this and will reach that limit by some corner cutting scheme where the angles flatten out, they go to 0, and I reach a limit that has corners. So let me put it down. It means basically we can obtain any convex curve, in particular with corners, of course, under some angle flattening cuts with, and we try to be minimal here with what we do is here we cut just one corner. So I call it also an edge preserving cut or one corner cut with a one corner. And if I move this edge, then I cut one edge. I only cut one edge cuts. Okay, so there is a counterexample. We need to restrict our cutting. That means to these edge preserving cuts. We are not allowed to cut too much. Otherwise, we have difficulties at least to prove things and somehow to say what kind of cutting is useful then for us. So this is now what I want to generalize to polyhedra. And first we observe, well, if we go to polyhedra, we cannot preserve the edges, of course. The edges, they stand for corners. If we go back here, if we are along such an edge, of course, then there will be always a corner. So we need to cut a little bit more. And what we do is then we say face preserving instead of it. So we take that out. And then we have that theorem, and still true, because it's an if and only if, for instance, we had the angles not going to 0, then we have a sequence of points with angles that are greater than some amount away from 0. And since we cut convex sets and the next polyhedron that we get is within the old one, we have something within a compact set. So that sequence we can generate with the big angles has limiting points, and that means the limiting surface has points with an angle that is bigger than 0. So there would be a corner that is one direction, and the other direction is if the limiting surface has a corner and the angles flatten out, then there must be a polyhedron that has small angles compared to the corner that we have. That means that there must be several faces of the polyhedron that touches that corner. So that corner has several faces of the polyhedron that are tangent to it. And these contact points that we get on the faces, if we do face preserving cuts, they would be in the interior of the faces because we cut the edges, we cut the boundary of any face. So at the end, it could not be that we have a contact point that sits on the boundary, but if there are several faces touching a point, the same point, the point necessarily lies on the boundary, on the edge of two faces where they meet. So this is a contradiction, it doesn't work. So this theorem is kind of simple to generalize to surfaces. Well, here we have the counterexample that if we would cut more than an edge, in case of curves, then we run into problems. Then this doesn't work anymore. And we could do the same also for polyhedra. What we do then is we can cut, we can move the edges. So we would say here for any convex surface then, but we have to take out the any. If you go to, and this is one thing I will explain, a thing that is different than in the plane, your convex surfaces with corners under angle flattening cuts with, now instead of the corners, we need edges, and instead of the edges, we need faces. We need to go up by one dimension. So this is edge and face, one face cuts. Then it would still be true. And why did I take out the any? If I move these edges, that corresponds then, if I go to the polyhedra, I move faces. And if I do it, then the following happens. Here you see that cut, which I did here. And this cut is parallel to that cut. So if I cut instead of here, I cut there, I would get another polyhedron. It is parallel. All the faces that we get, they are parallel to each other. However, here, if I cut deeper into the polyhedron, I get an edge that has no counterpart in the other polyhedron if I cut here. So this changes the topology, and that means, can't go into too much details, this changes the game, and then it means that we cannot move the faces arbitrarily close to an arbitrary convex surface that we have in mind as a limiting surface. So therefore, we can do it only for many, but only for some of the convex surfaces. But for convex surfaces that have corners, we can do that. Okay, there is one thing, and the other thing is, of course, we need to do this angle halving. And if we come to polyhedra, that also looks a little different, or there's a little bit more to consider. Here's an angle halving cut, and it's always the exterior angles that we consider here. So there is two planes, and there's the exterior angle of the planes. And if we cut like this, we get half the angles there. But if we do it, well, if you do it in the right way, if you always take the sharpest edge and cut the sharpest edge, or one of the sharpest edges, then the maximum angle will go to 0. So this is under sharpest edge cutting. If we wouldn't do that, if we cut all the edges eventually, but not necessarily always the sharpest first, but first some others, and then we go to the sharpest, then the following happens. If we look at the Gaussian image of that polyhedron, that means we look at the normals of the polyhedron. The normals are represented by points on the unit sphere, and then we would get, for such a corner here, or corner here that we have cut, we get 3 faces that make that corner, and there are 3 normals that would correspond to 3 points on the unit sphere. So we see a spherical triangle where the edges, they correspond to the normals that we get if you go across the edge. These are all the normals on the edge that we have there. So there are spherical triangles. There's a spherical triangulation actually for the whole polyhedron, but here I have just one triangle. If we now half an angle, that means here is an edge. We go to the midpoint, and then we have a new face there, and we have two new edges. One is here, so we get a splitting in this spherical image, and here's a neighboring triangle, and there we get another edge. So that would correspond here to this edge that is new, and there's another one, this is new, this corresponds to that one. So we introduced a long angle here again. And if we then decide, well, we first cut here, we halve this edge, then we get another edge here. And then this is a long thing, we need to cut it. So we cut it in the second step, we do this here. And there's the long thing. Well, we decide first to cut here, and then we halve the long thing and go on like this. And that means we always have a long edge and we'll never get rid of it. And it will converge then to something, a big angle in the limit. So we don't get that the maximum angle would go to 0. We have to be a little bit careful of how to do it. Well, and then if this was in the plane, it is simple. If you always cut, or if you always bisect here the longest edge in such a triangulation, a planar triangulation, then the perimeter of the triangle is reduced by a certain factor and everything works. But on the sphere, this is different. There we have extreme triangles that if you split it like this, then the subtriangles, they have as big a perimeter as the big triangle that we started out to divide into two. So spherical geometry is more complex, and so the proofs become more complicated if we go to the polyhedra. Well, okay, let's see what we have. At least we have here no corners in the limits, under phase preserving cuts, and if we cut more than a phase, then we have a problem because of this counterexample. So we should cut not more than a phase. We should not cut more than these phase preserving cuts. However, there's one thing which we have to take care of. No corners does not mean C1 if we come to surfaces. So for surfaces, what I've written here was for curves, and now we go to surfaces, then C1 is only equivalent to having no corners and no pinch points. So there are other points that we have not yet considered, and these other points can be seen here. This is a pinch point. A pinch point is a point, you see the cube, and I rounded off the corners, the same thing you would do to get a dice. You have here a point with a 2-parameter family of tangent planes, with a one parameter family of tangent planes. It basically corresponds here to one of those edges. And here at that corner, we have a 2-parameter family of tangent planes. This is a corner. I should write this down, maybe 2. Here is a true corner. But here is a pinch point. So what about these pinch points now? If we go to this theorem, here we take care of the corners, but do we also take care of the pinch points? Unfortunately, this is not the case. One can construct any convex surface without corners under angle flattening. Corners, they don't show up because of this theorem, but with isolated pinch points under angle flattening cuts with, and now we have here phase preserving cuts. So we take all this out and have phase preserving cuts. So phase preserving cuts is even cut too much. We need to restrict the cutting further to obtain smooth limiting surfaces. And what we can do then, there's not much left. It is basically we can cut edges. So edge cutting is the thing we should do. And first I thought, oh, this is okay. Now I understand what we have to do for polyhedra. However, I was not able, or we were not able to really prove that under edge cutting, where the angles flatten out, we get C1 surfaces in the limit. So we don't know. And we also do not get a counterexample. This is an open question. We have to do something else. And this is the following. I try to mimic what I have here, that here the segments are bounded by what I see on the polygon. And what we do is here the following. Here you see a limiting surface. And here you see indicated at least a polyhedron. We have a sequence of polyhedra, and this is the kth polyhedron, pk, in that sequence. And here you see some faces of the polyhedron. And what I do then is I project the polyhedron onto the limiting surface by taking some interior point here as my projection center. And then I have a central projection. And the faces, they are projected into certain parts, patches of the limiting surface. So here you see the projection of that face. And this is a patch which I call pi. So pi lives on P infinity. And then we make the following definition. We say that this sequence of polyhedra that we have has what we call local normal control. That means there exists some integer such that for all these patches that we get, this is, I call it a kth level patch because it comes from a face of the kth polyhedron. So for all kth level patches, pi, there exists a disk around that face on that polyhedron, the kth polyhedron. What we see here is the face, and there are in yellow, the neighboring faces, and the face and the neighboring faces, they form the one disk. And if I then go to the next faces around it, I would get the two disk and so on. So there exists an R disk on that polyhedron pk such that the Gaussian image, so these are the normals, the Gaussian image of the patch pi, the normals that we get on pi, can be bounded by the Gaussian image of this R disk. R disk, we should give it a name, D. So the D there we have it. So that means we can bound the normals that we have on the limiting surface by the normals we have in this polyhedron. And if we can do this, then basically we can generalize here this theorem. Then we have that with local normal control, we get the following. C1 if and only if the maximum angle goes to 0. So this is quite simple, because if the maximum angle goes to 0, then we have for the R disks that the normal variation is diminished arbitrarily and then this is a bound for certain neighborhoods on the limiting surface. Every point has then a neighborhood with an arbitrarily small normal deviation, so it must be a C1 surface. So this is fine. And now we can ask, does edge cutting, where we just cut one edge at a time, does it have local normal control? And let's see what we can do. Here you see part of a polyhedron. These are the edges of the polyhedron. And now I cut an edge. I just cut an edge. So here you see the new face that I get if I cut that edge. Then I decide to cut this edge. And here is the next face that I get. And I continue doing this. So I go along that polyhedron, can cut also this and so on. And then you see, if I do this cut, the new face has a normal that lies in the Gaussian image of this edge. And this is determined by the normals of the 4 adjacent faces that I have. And that means the normal that I have in this new, here, the new face, it depends on this normal here. This normal, basically, this face, has something to say within this area. It influences this area. And this normal here then influences this normal influences this normal, and so on. And that means that any normal can influence something that is very far away. So we don't get this local normal control. So too bad. Then we think, well, we don't cut arbitrarily, we cut parallel to that edge. So the new normal that we get here, so this is basically normal, only depends on 2 neighboring normals. So that restricts this a little bit. And first you think, well, it works if you look at it, but then if you think more about it, you find there are problems. And it's difficult to prove that parallel edge cutting has local normal control. So this is too bad. This is an open question again. We don't know whether parallel edge cutting has local normal control. We don't know it. Don't have a counterexample, and we don't have a proof either. So next thing we can do is the following. We need to restrict it somehow in a different fashion. We do edge cutting in the following way. Here, we take a convex polyhedron, and you see when we cut, if we do the edge cutting, then we always get vertices that are of valence 3. So what we have, basically, we have graphs, edge graphs that are trivalent. All the vertices have valence 3. And these graphs, they are also bridgeless, so there are cycles for every vertex and for every edge. They have a perfect matching. That means there is a set of edges which is edges that are isolated, and all these edges then connect all the vertices. And this is the bold edges that you see here on the cube. There are 4 of them. They form a perfect matching. And now I cut the edges in that perfect matching. So first, we cut first edges, all edges of a perfect matching. So that means we have to do a cut here. We do another cut here of this edge. Here, the other edge has to be cut, and this edge has to be cut too. So after we cut these 4 edges, then we see there are some edges that remain, partly at least. Part of it has been cut here. This edge, if you look at it, it lost its endpoint here, and it lost its endpoint here, but there's part of that edge. And these remaining edges, they form a perfect matching again. So I can repeat. Now I cut all edges, and these edges These are the remaining edges, and they are classified by having lost their two endpoints. All edges that lost two endpoints, both of their endpoints. So I can repeat this. Since this is perfect matching, I cut it again. Then the remaining edges, these are the blue ones, are then, they lost both of their endpoints, and I cut them again. And so if I go on, I can cut all the edges and all the new edges that come up in the scheme. And this is what we call the 4/8 scheme, because what we get is when we cut one edge, we get a quadrilateral. And the quadrilaterals, as you can see here, if I cut the edges, they become octagons. And they stay octagons if I keep on cutting. So that means we have transitory quadrilaterals and persistent quadrilaterals. This is the name of the scheme. And if you dualize it, actually you have a topology, a subdivision topology with vertices of valence 8 and 4. And there's a 4/8 subdivision scheme. So it's also related to this topologically, at least. Well, and here you see that when an edge loses its endpoint, I give it a direction. It points to the endpoint it has lost. And what we can do, we can generalize this even and say, first, we cut edges not in a perfect matching, but arbitrarily, till all vertices are gone. So the initial vertices need to be gone. Then we have only new edges, or perhaps some edges that lost their endpoints. And then we keep on going, doing the same as we did before. And if we do this arbitrarily, what can happen then is that we get edges that have lost only one endpoint at some point. And these edges, if we cut them later on when they lose their second endpoint, they give us hexagons. These are also transitory hexagons. They become octagons later on. So there we get a 4/6/8 scheme if we do this. And now here we have a complete arbitrary cutting order. And this may be bad, I don't know, because of what we did here cut arbitrarily and I got into problems. However, what happens here is that the limiting surface, I call it P infinity, does not depend on the order, on the cutting order. And basically, what you see here are directed edges. And there are some edges that have two directions. They are bidirectionals. And some edges that have only one direction. And there are some edges that have no direction. And the directed edges, they form paths. So we have a forest of paths. The bidirected may lead into two directions, but then there come only one-directed edges. And these directions, they tell you in which order you have to cut them. There's no way out. If you do this here, you always have to cut it in this order. It doesn't work in any other order. But there are different paths. There's a forest of paths, so I can choose which route of that or which route I wish to cut first. But this does not really matter then for the limiting surface. We have some choices, we have some freedom, but it does not affect the limiting surface. So we can do it in certain rounds. We cut all the edges that we have, and then we cut the new edges that we got in cutting in the last round and continue like this. And that simplifies the proof. And then the second observation now is the following. We can consider the paths, these directed paths, as vertices. We group them into a virtual vertex of a graph. So we consider the directed paths as vertices. And what happens is astounding. You get a new graph, and this graph, and then we do a cutting, we cut all the edges, then we get a next graph. So we have a sequence of graphs, and these graphs have a topology as in the do7 subdivision algorithm. So we have a do7 subdivision, I would call it here topology. So the do7 algorithm is a tensor product scheme of this check-in algorithm. And here to say what it is we have here a face of a polyhedron and here the neighboring faces. And if we now do this do7 subdivision algorithm, we get new points here in that face. So we get a smaller face with the same number of vertices within for any of the faces. It look like this, and then they are connected like this, and so on. So for any vertex, we get a triangle around. For any edge, we get a quadrilateral, and then there are the old faces where we get a smaller face with the same valence. And for this scheme, for the do7 scheme, there are B-splines behind, quadratic B-splines actually. For that, we have local normal control. This is known for the do7 subdivision, although we are using different terminology there. But that means here, because it's only the topology that matters, here we also have local normal control. Here we were able to show local normal control. So now we are in business, cutting like this. The 468 scheme is guaranteed to always give us a C1 surface in the limit. Okay, now I switch my window and show you some pictures. Only need to find where I have it. You have to stop that first. Okay, this does not really work. Can you see my aya? It should be.
Yes, we can see it.
Okay, now I can't see it anymore. Okay, here it is. So what we did is, here's an implementation of the 4.8 scheme. You see the limiting surface. It doesn't look that nice. Although, after several attempts, we tried to do something optimal. We tried to optimize the Gaussian curvature, and it worked in other cases that we had, but here didn't. There's some reason for it. So we did something else. Here we averaged the normals, and then we learned, and we get to a nice sphere actually. And what you see here, these are the white ones, the white faces that we have here, they are actually octagons. Only there's some edges that are very small, so you can't really see them. And the black, the blue ones here, they are the quadrilaterals. Some of the quadrilaterals are also white. White means they touch the sphere. This is where we want to go. But the quadrilaterals, they don't touch. And in order to make them touch, we need to move them to to the sphere. So what we do is we extend our scheme by non-phase preserving cuts. These were the bad cuts. But what it means is if we move that phase, we don't change the normals. And if we do this only once or maybe twice or a bounded number of times, this does not affect local normal control. We still have local normal control. We are only not allowed to do it infinitely often to move the phases. So there we learned that we have to do something more. We also have to allow non-phase preserving cuts, and then we get these nice results that you see here. Well, this is to show you here we have another perfect matching. I showed you a perfect matching where we took here the vertical edges of the cube as a perfect matching, and here we take vertical edges and horizontal edges, two horizontal edges, and now we take here maybe these horizontal edges, and then the other ones go in a different direction. This would be a perfect matching. And then what happens after 3 steps, we had to stop because there are some angles are so flat that we had numerical problems to go on. So I really don't know. This is also a tricky business of how to start it. And here you see this for a dodecahedron, which we cut. And after 4 steps, we also had these numerical problems. And you also see there's some unevenness in the patches, in the patch distribution, in the sizes. But then if we first do another step here, where we cut all the corners, this is a square root of 3 cutting scheme, another one that we have, and then do the 4/8 scheme, then things work. So somehow we don't know how to do it automatically, but we need a well-distributed phase size for the polyhedra to get good results in the limit. So this is for spheres, but then if you try to get an ellipsoid out of this cuboid, you see it's not that simple, because what we did is Euclidean. If we take an affine image now of it, it would not work in the same way, and there is also not such a good phase size distribution that you can see here. The result looks kind of okay, but there are still things that we need to explore and to understand better. Well, there is one more scheme, the square root of 3 cutting that I said. There we would cut all the faces at the same time, so that neighboring vertices that have been cut get faces that are adjacent along one edge. And this is dual to the square root of 3 subdivision algorithm, at least topologically. You see the surfaces that we get in the limit, they are a bit bumpy, so we need to do a little bit more. We can take the sphere again, but if we push the faces to the sphere, then here things happen that the topology is not consistent anymore. So we pushed it too far and we needed to do something else. So we took them we dualized it, took the square root of 3 subdivision algorithm and optimized things by this umbrella scheme. And then this leads to a good normal distribution and also to nice results that we see here. Well, one more scheme, the last one that I have is the honeycomb scheme, where we cut all the edges at the time, but this does not really fit into what I talked about before. So these are not edge cuts. They are all, because we cut everything at the same time, they are not isolated then. So it's a little different but this one is also simple to prove, because there's a dual scheme which one can use to really prove things. Well, don't say something about this dual, but end here by an acknowledgement. There are the students who did the pictures, and Ijin Xu is the one I'm discussing these things with. So this would end my talk. Thank you for your attention. Hope I did not go for too long. See, time is a bit far.
Thanks very much. Thank you, Professor Prautzch. So I'm trying to put the uploads in my. Okay, yes. I'm applauding. Thank you. So please, the time for questions. So if you have questions, please make your handwriting, or you just can do it by voice. Maybe I have one question, like mathematical, one historical. So maybe I will start with a short discussion. I have one historical question. So George Derham, yeah, who first, I think, to the best of my knowledge, he was the first who studied the key cutting angle algorithm for curves with the constant ratio. In the late 40s, he was already world recognized mathematician. So he was in the gold age of his career, and he was invited to Harvard.
Oh.
And in Harvard, and then in Princeton Institute for Advanced Study. And for these 3 years, he suddenly got interested in this subject. Mm-hmm. Which seems to be quite elementary after what Derham did with cohomology and Riemann surfaces, yeah, and Riemann manifolds. And he wrote 3 papers about these cutting angle algorithms with the constant ratio in all iterations. So just historical question, do you know why, what are the reasons of his interest? I didn't find any explanation in his papers why he got, or he just predicted future applications. But
yes. Yeah, Carl de Boer was the one who found out about the papers, and he's mentioning it in his paper. The papers are in French, and it is said, I really don't know if it's in the paper, whether Derham says it himself. He got interested by a very practical application. There were carpenters, or I don't know if they are called carpenters, tool makers for hammer. For hammer, if you have the handle of a hammer needs to be around it. And these people were using basically what I've shown you in the beginning. They took here alpha and beta to be 1/3. And this corresponds to this point here. It's just on the border of it. And then he got interested in it. And the first paper is just with that scheme, I think. And asked himself, I don't know why he asked that himself. Is it a smooth curve in the limit? And he then also generalized it a bit, but Gregor Chu then had the most general formulation of it. They were not aware of the Derham papers, but so this is all I can say about it. There is this really practical application by people who didn't have corner cutting in mind. They didn't know about C1, but they just did it. It worked for them. And yeah, and why should even a genius not do simple things and get interested in it?
Thank you. So please, Thomas Meister.
Live on bread and water. This is.
Thomas.
Sorry. I have some questions, and why? Maybe I missed it. Why are you not cutting the corners of the polyhedra, but always the edges?
If I cut the corners, if I cut the edges, I also cut the corner. And if I only cut the corners, maybe I do it here. I cut a corner, I cut a corner, I cut a corner. What you would see then in the limit, you would get, this is corner cutting, then a planar corner cutting here on the face. You get such a limiting curve, and there's a point that you would not cut away if you only cut the corners. And this is a pinch point. So here we don't get C1. So that means we need to cut more than just the corners. And if we cut the edges, we take care of the corners as well. So we don't have to do corner cuts in between. It's sufficient to just cut the edges.
And related question, why are you cutting all edges simultaneously?
Why do I do this simultaneously? Yes, this is the, here. If I do it one by one, that has the disadvantage that the influence goes across the complete polyhedra. But if I cut, and I cut not all the edges, I cut half the edges at one point and then the other edges in the next step. And that prevents these things because there are two edges, or we come from two sides, and we block the cutting for all the edges. So the influence of one edge in the normals gets blocked by the other edges. So cutting everything at once, or basically simultaneously half of it, helps to get this local normal control. And here for corner cutting, if we go to the curves, for Gregorian 2, you also did cut it all the corners at the same time. This result then by the Bohr is a little more general. You can cut whenever you like. You only have to make sure that eventually every corner is cut at some point. And at least here for the 4/8 scheme, for the 4/6/8 scheme, we formulated it also in a way that is general, so we can cut whenever we want, but there's a certain restriction on the edges that we can cut. So there must be something fulfilled before, and this is basically the thing that helps you to bound the influence area of a cut.
That I think you didn't understand me, maybe the connection. I understand that you that you don't want to cut all in one after another. So my question is, why aren't you always cutting simultaneously all of the edges? So it seems to me, even in the 4/8 scheme, you're cutting one edge after the other.
Well,
but in a way that they do not influence each other.
yes.
But in the picture from before with this chain, you could also cut all edges simultaneously, and then you get in the areas where they overlap, you get maybe new faces.
Yes, if if I would do it simultaneously, yes, then I get certain topologies here in the overlapping area that are more, I don't know, this is, if I let this depend on it, yeah, possibly this could work, but I don't know about the topology, what could happen then there.
I understand.
I don't know, this is always a little difficult to visualize and then to think about it, and then easily you think it works, but then thinking more about it, you see, there's still a problem with it. So I try to indicate that there are some problems where we really, we tried hard, but where we really have no solution yet. And maybe this is a good point that you made, but I need to think about it. It's certainly not a thing I can settle in a minute.
Okay.
Okay, more questions? I have one short question also. Harmut, am I correct, or I'm just maybe I'm confusing, that I read about the normal control conjecture of the cutting, of the age cutting in 80th? No, it was, I think that at the date of 80th, I already read about it, or maybe I'm mistaken.
This I don't know, 80s? What?
80th, I mean 30 years ago.
3 years ago, yes.
Yeah, it was there, yeah, because I remember that one of the papers. Could you repeat the statement, yeah, of the conjecture?
With the local normal control, I mean.
Yeah, of the edge cutting, yeah.
My conjecture is that parallel edge cutting has local normal control.
Has,
but I'm at the moment, I think it's 60% yes and 40% no.
But for the last 30 years, there's no progress.
Well, we made progress on the 4/8 scheme and with the 4/6/8 scheme and the 2/7 subdivision topology, and we understand this much better. And also, this is lately what we understood, that we really needed to do this parallel phase cutting, which I thought we should not do because it contradicts all the other proofs of where we had the counterexamples. But if you do it in a controlled fashion, it is helpful. So we understand it better, and I had more students who program things, and then it, well, takes a while.
Okay, thank you.
Vladimir Yurievich, can I ask a question? Baradim Piotr.
Yes.
Yes.
Professor, are there any estimates for the rate of convergence to the limit surface or to the limit curve?
Yeah, no.
In Hausdorff metric, maybe.
Yes, there's none, and I think we really don't have something like in subdivision. We often have quadratic convergence if you take the check-in scheme and so. But here, this is only a suspicion. I think it is less because we do it so arbitrarily. And well, for curves, it's always easier to say. I mean, if I have two tangents and the contact points, then I can basically bound the distance, and I get quadratic convergence, quadratic then in the distance of the contact points.
Yes.
But for surfaces, this distance is difficult to estimate because there's some global business going on. If I cut, I can cut at one point, and then the face by which I cut goes underneath many other faces, and it could have some global thing is going on. And so the face that I get by cutting is then adjacent to faces that are far away. And this is something difficult to rule out. Maybe
so this is a problem.
Yes, and possibly we could say something about a scheme like the 4/8 scheme and could think about it. But this is a point we so far had not really looked at. We had more difficulties to get the scheme itself, and conversions may come later.
Thank you.
I have to leave something for other people to do.
Okay, thank you.
But just related to the last question, so this is well known that for like usual linear subdivision schemes, yeah. For example, for curve design for univariate, the speed of convergence, the rate of convergence is entirely determined by the smoothness of the limiting curve.
Yes.
And what is this
what
rate,
about-
Vladimir Ilyich, what is this rate?
The rate of convergence is linear. I mean, that's exponential. Some q to the power of k, where k is the number of iterations and q is smaller than 1. And
Very rapid convergence.
Yeah, this is the rate of convergence to the limit surface.
Mm-hmm.
And
But you are talking just about the points, not about the polygon.
about the points, yeah, yes. What about, I mean, the rate of convergence here? So does it depend only on the smoothness of the limiting surface, or it can happen that the limiting surface is extremely smooth, but the convergence is slow?
So I think this is, we have these contact points. If we do this edge or phase preserving cuts, we have the contact points. And if we talk just about the points, then the points sit on the surface. This is convergence in one step. So we are talking basically about the polygons, and then quadratic convergence is the best we can get, or basically, and related to the differentiability, the smoothness of the limiting surface is something here. I think we can go up to C1, but it would be difficult to get C2 or even smoother surfaces. And I'm not sure what the reason is, but there's a paper that says basically that within the C1 surfaces, the C2 surfaces form a meager set when it comes to the convex surfaces. So it's very difficult to get to C2 surfaces. And with what I did, I think it's not really possible to say something about higher smoothness. For higher smoothness, I would need a parametrization, I think. Otherwise, I would not really get there. I mean, could talk about curvature, maybe discrete curvature, and say something about curvature continuity then. But higher derivatives, I think, is out of the question with the way we do this here. And so I could not relate higher smoothness orders to convergence orders. This is, as far as I can see, impossible for here, or never should say impossible, but don't see how to do that. Yeah, and otherwise it is, if we just look at the points, yeah, it's, if we have these contact points, it's fine, then we are just on the limiting surface. But then if we look at the tangent planes there, then it's basically the distance, and that needs to be estimated.
Mm-hmm.
It's not what we have done. So it's the distance of contact points on that surface that basically determines then how quick we converge.
Thank you. Thanks very much. So I think now thank you, Professor Prautzch. Now we pass to the next talk.